Actually, before I go to this paper, let's go back here. And here we introduced class activation maps. But to get the class activation map, we had to change the architecture, the last few layers of the architecture, remove the nonlinearities to end up with a linear structure at the end. But then this one is going to need a little bit of fine tuning. So you need to do retraining a little bit. Once the training is done, then you can start visualizing. The next paper is going to come and say you don't even need to linearize the last part of your network. This could be still fully connected with a bunch of nonlinearities after the last convolution, and you still are able to visualize. And how can we do that? So I don't want you to panic when you see this figure, because I'm gonna break this apart. And the way to read this figure is this. There is an input image. You have your convolutional part of your neural network. You take the input, you push it through convolutions, and in the end, you're gonna get a bunch of convolutional feature maps, and these are your convolutional feature maps after applying ReLU. So these are rectified. So we are here now. The previous paper had a global average pooling here. Now we are going to have different tasks, and let's focus on image classification for now. For image classification, you usually have a bunch of fully connected layers. For instance, in VGG type of networks that we covered, you had these fully connected layers. And in the end, you get the classification score for each of your targets. Now what you can do is pick a target, take the derivative of that with respect to these feature maps here. This is a one-dimensional function taking a high-dimensional input and outputting a single scalar. So you can take its derivative using backpropagation. So you're going to backpropagate, and in the end, you're going to end up with a matrix with actually a tensor that's going to have the same size as your rectified convolutional feature maps. And that one is being plotted here. So you're going to backpropagate till this point, and that's going to give you these. Now, what you can do is you can do a global average pooling on each of these backpropagated feature maps, and you can end up with a bunch of scalars. Now you take those scalars, multiply them by your original feature map, add them together, apply a ReLU, and that's going to give you your Grad-CAM. So let's go through the math. So don't worry about the rest of the figure. I'm going to explain that later on. So what does Grad-CAM stand for? It stands for gradient weighted class activation mapping. So grad stands for gradient. And in the end, we are going to end up with a class discriminative localization map, which is this plot that you're seeing here. But how do we get to that? You take the derivative of one of your classes, the score for one of your classes, for instance, a tiger cat, and you take the derivative with respect to the feature map, and that's going to give you a bunch of derivatives, and these derivatives correspond to this part of the figure. Now, to get alpha ck is these W1ck, WICKs. So there is a discrepancy between the figure and the notation, but it's not that big of a mistake. It's just a typo. So these alpha ck's are WCKs, and they are coming from doing a global average pooling on these derivatives to give you these scalars. Once you get the scalars, you can do a linear combination of those scalars and your feature maps, the original feature maps. You do a summation. That summation corresponds to this part of the figure. You do a ReLU because you are interested in the positive influence of that particular pixel on the class, and that's going to give you the visualization that you're interested in. So that's going to give you this. After you increase the resolution, because the resolution is going to be 14 by 14, then you have to increase the resolution to the original resolution of the image. Now we were interested in a target cat, and in the end, we are focusing on the target cat. Yes, go ahead.
So here you talked about this positive influence, and so that's like where the heat map is strongest. That means that is like very important for this class.
Exactly.
And would negative influence just be that it's very unimportant for that class, but we just don't care about that?
Yes. For instance, maybe that window over there is going to have a negative influence, but we don't care about it. Okay, perfect.
To ask that again, so if you had a negative gradient, it'd be something where like the presence of this part of the picture detracts from the probability that it's a dog or detracts from the probability that it's a cat?
Yes, that's correct.
Okay.
Actually, that's a good exercise. If I were writing this paper, I would visualize that as well.
Because it seems like both are important, like positive evidence towards one class, but also making the other probabilities in that softmax smaller so that the one that you care about is larger in comparison.
Yes, that's correct. So I think that's also important to visualize that as well. But for now, we want to see which parts are having a positive impact on the class target, tiger cat. And that's doing the correct thing now. You can see that it's visualizing the correct part of the image. Now let's see some more examples. This is the original image. This guided backpropagation is very similar in terms of concept to the visualizations that we saw here. So there is going to be backpropagating through the entire network to the original pixel level, because these operations are nothing but backpropagation. This is the forward pass, this is the backward pass. And that's exactly what we are visualizing here. These are guided backpropagation for the cat, for the class cat, guided backpropagation for dog, and that's this part. I know it's a little bit blurry, but the guided backpropagation is giving equal emphasis to the face of the dog and the body of the cat. Now, if you take that and multiply it, literally you're multiplying point by point, pixel by pixel, you're going to be able to pick up the cat, and that's going to be guided Grad-CAM. So this is guided backpropagation. This is the output of Grad-CAM. It's exactly this LC of Grad-CAM that you're visualizing here for the class cat, for the class dog. Now, if you take that, multiply it by B, basically you are multiplying B and C, and that's going to give you your guided Grad-CAM, which is focusing on the cat, and the other one is focusing on the dog. And this is just another way of doing visualization. This corresponds to what? This corresponds to this plot here, where you had your occlusion, your square, and then you were sliding it over your image. So that's exactly what we are seeing here. And not only it works for VGG, it's going to work for ResNet and other types of networks. And you don't have to retrain. What else? We covered the classification before we move to image captioning and visual question answering. Why is Grad-CAM a generalization of CAM? This is the score corresponding to a class when you had CAM, basically global average pooling. Now, if you take derivative of SC with respect to the feature map, you're going to end up with these W's. And if you remember for CAM, we were switching the role of the summations to give us LC CAM. And in the end, Grad-CAM is a generalization of CAM where you have your alphas to be W's. So is this clear? If everything is linear and global average pooling is linear, then these derivatives, there is no nonlinearity, and alpha CK is going to become equal to WCK. And that's why this typo is not that big of a deal, because in the end, they're going to end up being the same thing if your model is linear from this point on. Now you can do image captioning and visual question answering as well. For image captioning, the output of your convolution is going to go through a fully connected layer, and then it's going to go to through a recurrent or LSTM, which is going to give you the probability of this sentence. And this probability, you are going to break it down using the chain rule for probabilities. So don't worry about it. But in the end, you're going to get a log probability. You can take the derivative of the log probability with respect to the feature maps, and that's going to give you your derivatives with respect to the feature maps that you can use to obtain alphas and your Grad-CAM in the end. Now, if your caption for this image is a group of people flying kites on the beach, then your network is gonna focus on these kites. There's a kite here, there is another one here, there's another one here. So it's focusing on the kites, and it's also focusing on the beach and this part of the beach. If your underlying caption is a man is sitting at the table with a pizza, then your network is gonna focus more on the man, and it's gonna focus on the pizza as well. You can do visual question answering. For visual question answering, there is a question that goes in, and the question is there a cat? You push it through a recurrent neural network or LSTM, you get some features. You get the features of your convolution, you concatenate them, you push them through a fully connected layer, and in the end, you answer your question. Is there a cat in this picture? And the answer is yes. You can take the gradients of yes and back propagate it to get these features that then you can use to visualize. For instance, if this image and this question goes in, so what is the man doing? And if your answer is surfing, then the network is going to focus on the man and some parts of the wave. And what is she doing? She's having a baseball bat, and then it's going to focus on the baseball bat. What is that? And that's an elephant. If that's the answer, it's going to focus on the elephant. What is that? If your answer is zebra, it's going to focus on the zebra. So any questions about visualization and understanding before I move on to the next one, which is about transfer learning?
For the question answering ones and the image captioning, do they have to prescribe a set of output sentences, kind of like with when we were doing image classification, there was like 100 classes that were prescribed beforehand, or does it learn that?
The actual task is learning it. For instance, the actual task is going to tell you, if you ask your network what is the man doing, it's going to give more probability to surfing. But when you want to go backward, you have to specify the outcome the same way that you were specifying the target cat when you were doing your visualization for the target cat. The forward pass is going to do it. It's going to, if you tell it what is the man doing, it's going to tell you it's surfing or he's surfing. But when you want to visualize it, you need to say, okay, I believe your answer is baseball bat. I'm going to give you baseball bat. And now you tell me where you're focusing. I want to understand why you gave me this answer. Okay.
Yeah. But then like all of the other networks, if we gave it something like a task which was outside of the task, outside of the, like in this case, they're all activities. They're surfing or eating a pizza. If we gave it a new, whatever kind of thing was happening, skateboarding, it wouldn't know the word skateboarding yet. Those labels of the activities have to be provided in the training data, right?
Yes.
Okay.
But the image caption, you can give it any caption.
You can, yeah, you have to provide it a bunch of captions. So then it learns like a corpora of captions that are plausible.
Yes.
Okay. That makes sense.
Any other questions? So this is really interesting. Your network is predicting something. Now your question is, why did you give me that answer? What did you see in the image that makes you think that the guy is surfing? And then that's what the image is saying. The network is seeing. It's seeing a guy and it's seeing some wave. And then it's telling you that the guy is surfing because of this. So it's no more a black box. You're seeing what the network is thinking. That's what I was saying. Neural networks are no more black boxes. You can actually open the black box, take a look, and yes, they were black boxes in the 1980s, but not anymore. Okay, let's move to the next topic then.